Good day. Today I'm here again to present one of the basic topics in our foundation mathematics MTH 111, which is surds. This basically arises from numbers that do not have exact square roots. For example, if we have root 36 now, that one has a perfect and exact square root, which is 6. Root 16 also has a perfect square root. The numbers such as root 3, root 5, these are irrational. They don't have a perfect root, perfect square root. Therefore, we refer to this as surds. This is exactly what we call surds. Now, just like we had in our class for indices and logarithm, we have rules. We also have for surds. Rule number 1 is when we try to multiply two different surds, the root of that one, we can separate them as we have it. Number 1, number 2, 3, 4. I think those ones are straightforward and self-explanatory, especially this number 3, root m by root n, we have m. Because from our initial class, from the class of indices, we stated that root m multiplied by root m, for example, because root m is directly equals to m raised to power half. So that implies that from our first law of indices, if we now have m raised to power half multiplied by m raised to power half, we have the basis to be the same. Therefore, we can perform operation on their powers. So this will be m raised to power half plus half. Straightforward. That one will give us m raised to power 1, which is our m, as stated in the rules guiding surds. Of course, this, when we have like surds, we can also have their coefficient as we have it in the fourth law. From this, we will take some few examples to apply all these laws of surds. You can see they are very small, just 3 or 4. For example now, let me pick some few examples and see the applicability. If we want to take the square root, the root of 18, for example, we can reduce this. We can simplify it. Root 18, for example, can be simplified further. Because what's our target here? We are looking for a number or a factor of 18 that will have a perfect square root. Okay? If we look at 2 times 9 now, this will also give us 18. And the root of this, from the first law, this will give us root 2 multiplied by root 9. And we know that the square root of 9 is 3. Therefore, root 18 will give us 3 root 2. This is the reduced form of the square root of 18. This is what surd want to give us. We have also what I call the arithmetic operations: addition, subtraction, multiplication, and division. These are the basic arithmetics. So we'll consider addition and subtraction. For addition and subtraction, if we have root 18, for example, we want to add it to root 8. And also subtract root 50, for example, from this. Of course, we have treated this. This is 3 root 2. The same way we treated this, we can also apply the same to root 8. If we multiply 2 by 4, we have 8. Okay? So, this will equally give us, we know that if we have 2 by 4, this will give us 2 root 2, because the square root of 4 is 2 straight away. So we have 2 root 2 minus, the same with 50, root 50. I think that should be 2 times 25, because 25 has an exact square root. Therefore, we have 5 root 2 for this. If we look at this, you can see that we have root 2, root 2, root 2, and that implies that our last law there can be applied here. So we have 3 plus 2 minus 5 root 2. Oh, I didn't even take note of this. I just picked this because this will be 0. So our result here will be 0. Now, having said this, we have some basic sorts, the ones that are not reducible. If we have root n, for example, and our n is 3, or any prime number, 7, 10, for example, because they do not have factors that can have an exact square root. For example, if we have root 10, what can we reduce root 10 to? Nothing. Because when you say 2 times 5, 5 does not have a perfect root. Rather, the same way, 2 does not have. So these ones are basic sorts that cannot be reduced. And so on like that. Also, I haven't said, I think we have mentioned, from our arithmetic we have mentioned addition and subtraction. Before we go to division, something is very important here to be defined, which is the conjugates of solve. So I'll call that conjugate solve. This is done by merely changing the sign. Conjugate solved. This is done by merely changing the sign from plus to minus in simple language. For example, if we have root A minus root B, the conjugate of root A minus root B will be root A plus root B. Also, if we have A plus root B, for example, then the conjugate of this will be A minus root B. That's that about the conjugate of sorts. Even if we have in other areas of mathematics, like complex numbers, we also discuss about conjugate there, and it is the same concept across board. By merely changing the sign. If it is minus, we change to plus. If it is plus, we change to minus. Now, this is done because in order for us to take the division part of this arithmetic, it is necessary for us to take this division because we are going to take the conjugate of the denominator before we can perform any operation. And also, let me mention that division is defined in another form, which is now the rationalization of sorts. How do we rationalize sorts? If what we have in the denominator is an arithmetic such as A plus or minus root B, if we have A plus or minus root B as our denominator in any given quotient function, then we have to change the sign. We have to take the conjugate of the denominator. We use it to multiply both the numerator and the denominator. But if what we have there is just a singular surd number like root B, that implies that we're going to use that to multiply both the numerator and the denominator. Let me demonstrate. Now, if I want to rationalize, because for division of surds, if I want to take this one now over root C, you know this is division. So what I'm going to do is, because the reality is this factor, this surd factor, I want it eliminated from the denominator. You can hardly perform operation when you have a rational number in your denominator. Now, I have to multiply this by root C and the denominator also by root C. By so doing, I will eliminate the surds in the denominator, and therefore we have root AC over C. We can perform operation easily with this. Okay? So, by extension, if we now have addition or subtraction of two surds, for example, if we have root 3 minus root 2 over root 3 plus, let's say, root 5, for example. If I want to rationalize this, what do? I take the conjugate of the denominator. The conjugate of my denominator is root 3 minus root 5. We will use that to multiply both the numerator and the denominator as presented. This will be root 3 minus root 5 over root 3 minus root 5. So we just have to expand this, and that will be all. Root 3 by root 3, that's 3. Root 3 by minus root 5, that one is minus root 3 by 5. Then minus 2 by this, that will be minus 2 by 3. And this guy now by this guy, we have plus root 2 by 5 over this one now, 3 by 3, root 3 by 3, we have 3. Root 3 by minus this, that's the beauty there. We have, maybe I should write it out. We are going to have minus 3 by 5 plus this guy by this guy now. That will be root 3 by 5 also. Then 5 by 5. That will be minus 5. This will give us, this by this, I think this one is 15. 6, 10. 3 minus root 15 minus root 6 plus root 10. All of these divided by 3 minus 5, because this one will go, it will give us 0. And this is what we want to achieve, that the denominator, we no longer have a surd, because it is an irrational value. We don't want to have it in the denominator so that it will be easy for us to perform operation. Therefore, the result here, I didn't choose something that will give us something light as our solution, but at least you can see from the denominator that this will give us 3 minus root 15 minus root 6 plus root 10. Because if we want to reduce this, there's nothing we can reduce root 15 to. This is not reducible, this is equally not reducible. So we leave the answer like that, and this will be over minus 2, which will be our answer. Root 3 minus root 2 over root 3 plus root 2. Of course, rationalizing this, we can equally use brackets. Root 3 plus root 2. This one also multiplied by root 3. Sorry, minus. We have to take the conjugate of the denominator. Root 3 minus root 2. We expand this and we have our answer straight. 3 by 3, we have 3. Minus root 3 by root 3 minus root 3 multiplied by minus root 2, that will be minus root 6, that is 3 times 2. This guy now by this guy, that's also minus root 6. And root 2 by root 2, that one is plus 2. And this will be root 3 by root 3, we have 3, root 3 by this, we have minus root 6, root 2 by root 3, we have plus root 6, so that will take care of that, and we go straight. Minus root 2 by root 2, that will be minus 2. Therefore, all of this now will be, we can now collect the like terms, because this one is a constant, this is a constant. 3 plus 2 now, we have 5, root 6 by minus root 6, because they are like surds, we can perform operation there. It's just like saying variable x minus variable x. Okay, because they are the same, so we can have minus 2 root 6 over 1. This will be the required result. You can see that one is very straightforward. Now, some other form of surd we can simplify. Let me also take at least one more example here to rationalize. Don't be scared by this. Don't be. Because it is very straightforward. We want to delve into trigonometry a bit. If we want to simplify 1 minus cos x, for example, over 1 plus cos x. Same way, what we have done earlier on, we just rationalize this. Don't forget, the definition for rationalization is by taking the conjugate of the denominator of any quotient form of surd, using it to multiply both the numerator and the denominator. That is what we want to do. By surd way, we have rationalized. So this is the same as root 1 minus cos x over root 1 plus cos x. And now we can rationalize this. Therefore, rationalizing this, we want to take the conjugate of the denominator, which will now be root 1 minus cos x multiplied by root 1 minus cos x. All of this divided by root 1 plus cos x multiplied by root 1 minus cos x. We have taken the conjugate of the denominator to multiply both the numerator and the denominator. The rest here is just arithmetic. And now, from here, this guy multiplied by this guy, because what we have here is exactly what we have here. That will be 1 minus cos x. Straightforward from our third law. Now, the denominator, root this by root this, you know that one implies that we have the square root of 1 plus cos x multiplied by 1 minus cos x. Very straightforward. The rest is just arithmetic, like I have mentioned earlier. From here now, we just need to expand this guy, and we have 1 minus cos x over, once you have a denominator, I don't know if I should jump or I should take it one by one. 1 multiplied by 1, we have 1. That would be root 1 by 1, 1. 1 by minus cos x, we have minus cos x. Cos x by 1, that will be plus cos x. And now cos x by minus cos x, that will be minus cos square x. Okay? And from here, this will give us 1 minus cos x over, this will go minus cos x plus cos x, that's 0. So we're left with 1 minus cos square x. Root that, the square root of 1 minus cos square x. Don't forget, from the knowledge of our trigonometry, the first identity that is proved here is that we have sine square x, because we're using variable x, and let me maintain that, plus cos square x is equals to 1. Recall that we have this as our first identity in trigonometry, and therefore sine square x will give us 1 minus cos square x. And this implies that, because we want to get the square root of this, sine x, by taking the square root of both sides, we have sine x equals to root 1 minus cos square x. So we will now come here and substitute this value for 1 minus cos square x. Therefore, this guy becomes 1 minus cos x over sine x. We have been able to take care of the square root in the denominator, and now we can perform operation. Of course, this is the same as 1 all over sin x minus cos x over sin x. And we know from the knowledge of trigonometry that 1 all over sin x is equals to cosec x, and cos x over sin x, that one is equals to cot x. Therefore, all of this is equals to cosec x minus cot x. So if we are to prove that the question given to us is equals to this, that question can be framed that way, that we should prove that root 1 minus cos x over 1 plus cos x is equals to cosec x minus cot x, or we can just say simplify like we just did now. This will be the required result. Of course, like we had in our indices and logarithm class, we also have some equations in form of surds. Before I move to the next part of surds, I would like to mention that just in case you have any ambiguity in this trigonometry, as we have explained briefly here, you can look forward to the next video. That will be a comprehensive introduction of trigonometry. And after having said that, I would like to move straight forward to the next part of surds, which is some equation. Let's treat at least one problem here. This question says solve for x if we have root 2x minus plus 3 minus root x minus 2 equals to, let's say, 2. Now from here, we want to solve this problem solution. Of course, we can rewrite this as 2x plus 3 equals to 2 plus root x minus 2. What can we do to this to reduce this? If we square both sides of this, because I want to deal with this sort, I'm not comfortable with it. Now, if we take the square of both sides of this, we can start to name our equation. Name this guy 1. Squaring the both sides of equation 1, we have, this will give me 2x plus 3, which is equals to, if I want to square this guy now, that means I'm multiplying it by itself. Okay? Which will now give us, okay, let's take it out together. To reduce the number of questions we are going to have. Now, 2x plus 3 now is equal to 2 by 2, we have 4. 2 by this, we have 2 root x minus 2. This one by 2. So if we add that together, we have 4 root x minus 2. Of course, root x minus 2 by x minus 2, we have plus x minus 2. So we are reducing the surd in this now. We can now collect like terms. If I add this guy to this now, okay, you know we have 2x plus 3 equals to 4 minus 2. We now have 2 plus x plus 4 root x minus 2. I can collect like terms and put all the normal variables aside, leaving only the surd on the right hand side, so that we can perform the next operation. And that is not far-fetched. This will give us, we have 2x here already. When x crosses over the equation, it becomes minus. So that is reduced to x. We have 2 here. When it crosses over the equation, it becomes minus. So 3 minus 2 will also give me 1. As That implies we now have x plus 1 equals to 4 root x minus 2. I still want to remove this surd here again. So what do I do again? I take the square on both sides. By squaring both sides of this again, you know we now have x plus 1 square equals to this guy's square, which will now be 4 root x minus 2 multiplied by 4 root x minus 2. So this guy by this, we have 16. This one multiplied by this, the root will go, and we are left with what? X minus 2. So if I'm squaring this one also, that will be x by x, and I have x squared, x by 1, x, plus 1 by x, that is plus 2x, plus 1. We have this. Okay? And from here, I can just expand this to have 16x minus 32. I want to bring all the variable x together and separate the constant. This is now x, so this is looking quadratic already. This is now going to give us x squared, and if this one is crossing over the equation, it becomes minus as well. So 2 minus 16, we have minus 14x. This one is crossing over the equation, it becomes plus. So this will be plus 33 equals to 0. This is now quadratic. We want to reduce this now. We look for the two factors of minus 14 such that when we have this back. When we multiply, we have 33. I think if we had 11 to 3, minus 11 minus 3, that will give us minus 14. And if we multiply that, we have 33. Therefore, this becomes x squared minus 3x minus 11x plus 33 equals to 0. I want to factor x from this to x. We are left with x minus 3. I want to factor 11 from here. Minus 11, we are left with x minus 3 here equals to 0. And therefore, we can see clearly that x minus 3 is now common. We can factor that also. X minus 3. And here we are left with x minus 11. Everything equals to 0. When we have two things multiplying each other, and we have 0, one of them, either one of them will be 0. So we have x minus 3 equals to 0, or x minus 11 equals to 0. And from here, this implies that x is equals to 3, or x is 11. That will be the required solution here. So we wrap up this here, and in the next video, we will discuss how to compute the positive square root of surds. You know, this one, they're very scarce in textbooks, very, very uncommon. Okay, so this is an added advantage for our subscribers. And since we still want to continue, we want to further, what we want to discuss is still about surds. That implies that after we finish in the next video, we'll have the exercises for you to go and practice. Thank you.